Do you want to build a robot that can see in 3D? But with so many different 3D cameras out there, choosing the right camera can feel overwhelming. I mean, I get it. You want your robot to have the best eyes possible, but between Intel, Stereolab ZED, and DIY options, it's hard to know what actually works for your robot project. And here's the catch, the most people just copy what others use or grab the cheapest option, only to discover later that it doesn't really fit their projects. And that mistake can waste weeks and hundreds of dollars, and that's my story. The smarter move is understanding how each 3D camera works, what it's good for, and when to use it. So in this video, I'll break down 3 major options: Intel RealSense, ZED Mini, and a custom stereo build. So by the end, you'll exactly know which one deserves a place in your project. Now, if you're new to here, my name's Elia. I'm a robotics engineer and educator helping you land in the field of robotics smoothly. For your information, a regular webcam isn't enough for your robot. And that's because the world isn't flat, it's 3-dimensional. While AI can generate depth map from a single image, that's technically generated guess, which is okay, but robots can't just rely on these uncertainties. They need accurate depth because they have to interact with the real world. Also, even with this advanced research approach like this paper suggests, the DL requires too much computational resources, often time, and as a roboticist, we want to minimize it. Now, how to solve it? Well, think about it. Just like us, we have 2 eyes for depth perception, robots also need multiple perspectives. But here's the catch, sticking 2 cameras side by side isn't just always enough. Calibration, synchronization, and sensor quality all matters. This is exactly where people get confused when buying their first 3D cameras. So the question becomes, if the stereo vision alone isn't always enough, what kind of 3D cameras actually work best for your robot project? And before we jump into specific cameras, let me share something that will give you much stronger foundation in the computer vision. Because once you understand how vision really works, choosing the right camera, right hardware becomes much easier. A lot of people hit the same wall in robotics. They can hook up the sensors, but when it comes to making sense out of the sensor data like camera data, they get stuck. I know that pain. I wasted months on scattered tutorials that never connected the dots. That's why I built my Computer Vision course series. In Computer Vision 1, we start with the fundamentals, image processing, object tracking, and how features like ORB power SLAM systems. This is the foundation that most people skip and make everything else much harder. In Computer Vision 2, we go deeper. You'll actually build a custom stereo depth camera step by step. We'll cover the math, code, and with Unity simulations so you will get it, not just memorize it. And if you're coming from different professional background, Robotics 101 prepares you with the essentials like rotation matrix and gamma filters. The exact tools you will use later in the visual navigation. So if you want your robot to not just see, but truly understand the world, this course will save you time and frustration. Links are below if you want to check them out. So what's a 3D camera? At its core, a 3D camera is a tool that allows robots to see and perceive the depth. There are 2 main approaches. First, stereo camera. They work just like our 2 eyes, using 2 RGB cameras and then comparing the pixel differences left and right images to estimate the depth. Second, active sensors. These project rays, like infrared or even lasers, and calculate how long they take to bounce back from the object, and it calculates how long they take to bounce back, similar to LiDAR. For instance, Tesla relies heavily on cameras, while Wave leans on LiDAR. Both approaches work, but each comes with trade-offs in cost, accuracy, and robustness, and no one knows which approach will dominate in the future. And that's why blindly buying a 3D camera without knowing how it works is risky. So let me compare some real examples, starting with Intel RealSense camera. The Intel RealSense D455 is one of the most accessible Intel 3D camera for various applications. It uses 1 RGB sensor and 2 infrared receivers, giving it a depth range up to, I believe, 60 meters, and the setup is straightforward. You can grab the demo app right off GitHub, and as a developer, the integration is smooth with both Python and Rust. I like to use it with the USB plug fixture because otherwise movement can cause disconnections, but once mounted properly, it's reliable and simple to get running. This makes it a great entry for beginners and solid prototyping tool for more advanced projects. So RealSense is great for a medium-range robotics project, but how does it compare something like Stereolab ZED Mini? which takes a different approach. The second 3D camera is ZED Mini by Stereolabs. It is more advanced stereo solution, but it comes with both strengths and quirks. It has two RGB cameras just like our two eyes, and it comes with built-in calibration software. That means you don't have to manually measure the intrinsic parameters. It also provides multiple demo apps through its SDK. When I mounted on a drone with Jason, the ZED SDK handles positioning surprisingly well. But there's a caveat. This model uses rolling shutters, which causes issues for fast-moving applications like autonomous cars. Also, sometimes the setup can be a little tricky. CUDA versions, GPU drivers, and the Python bindings sometimes clash. Especially recently, NumPy upgraded its version from 1 to 2, so a lot of packages can crash, unless you set it correctly. And to make your life easier, I shared my Docker image down in the description section to save your time. So, ZED Mini is powerful and flexible, but installation and rolling shutter effect can be frustrating, which brings us to another option. So what if you built your own stereo camera from scratch? Building a custom stereo rig is cost-effective and surprisingly performs pretty well. I mean, if you know what you're doing. With these two low-cost monochrome cameras from AliExpress, I built a setup capable of 210 FPS, which means I can get more than 200 images per second per camera. After the calibration, which I cover in the detail in my course, you can generate the depth mask just like with commercial systems. Now, here's the truth. The quality of this kind of low-cost camera varies. It's not just resolution or lens distortion I'm talking about, but the sensor consistency. Out of the 4 to 5 cameras I tested, the CMOS sensor weren't mounted identically on the PCB, so I had to handpick the best two, and that's the trade-off with the low-cost parts. So if you want reliability, high-end cameras are always safe. But if you are experimenting, learning, or building a project where speed matters, a custom stereo build can still deliver some good result. Again, assuming you know what you're doing. I think over the past decade, I total spent several $1,000s testing, comparing the cameras and the lens. And the truth is, what works perfectly for one project often falls short for another. A car-mounted camera might be great for testing visual navigation on the road. However, the same setup will not necessarily work on the UAV or UGV applications. And that's the reality of the robotics hardware. Every project has its own unique demands. So today, we explored the hardware stack for 3D cameras, but hardware is only half of the story of the robot. If you want to know more about the software stacks of robots, like how frameworks like DoraRS can be compared with ROS, check out this video link here. And most importantly, make sure you subscribe to the channel so you wouldn't miss out the important news and tips about robotics projects. I'm Elliot, thanks for watching, I'll see you in the next one.